All right, welcome back, everyone. So this is where we left off, a second order ordinary differential equation. And this is something that we can actually solve by integrating twice. And I have my boundary conditions here. So a second order with respect to radius, and we have two boundary conditions in the radial direction. So we should be fine. We should be fine. Let's start integrating. Okay, let's start integrating. Which color should I use? I'm going to go with white. Negative s over k times r. Okay, I just did some algebra, which you guys are smart enough to figure out. Good. Very nice. So, my first integration. My first integration. You didn't see that? My first integration with respect to dr, with respect to radius, is going to give me negative s over 2k r squared plus c1. Let's use different colors for the constants of integration, shall we? c1, and that's gonna equal r times dt dr. Okay, and some of you smart folks out there already know that this is a great place to use your first boundary condition, right? And that's exactly what we're going to do. I think some of you got the sneak peek of that, but that's okay. That's okay. You guys can... I like when you guys look ahead. So this, you're going to get 0 plus c1 is equal to 0. Okay, I heard Gen Z likes colors. Maybe I'm wrong. Maybe I'm right. You guys can tell me. c1 is equal to 0. There we go. And this is the point where I say nice. Okay, this is the point where I say nice, because my r dt dr, now I'm going to switch colors again. Actually, no, never mind. Equals r dt dr is going to equal negative s over 2k times r squared. And this is where I can integrate once again, right? This is where I can integrate once again. But before that, let's just divide both sides by r. Make our lives a little simple. 2k r is equal to dt dr. Very nice. Very nice. Okay, good. So t as a function of r is going to be negative s over 4k r squared plus c2. And now we got to figure out c2, our second constant of integration. And for that, we're going to be using our second boundary condition. Our second boundary condition, our BC2. Okay, let me just write it here. Our BC2 said that at r equals d over 2, diameter over 2. That's just the radius of the wire. We have a fixed temperature. Let's call that T surface. So plugging this boundary condition in, once we plug this boundary condition in, we're going to get, all right, what are we going to get? We're going to get T surface is equal to negative s times, let me just skip some algebraic steps, because I think my audience is really smart. 4 times 16k, very good, plus c2, very good, very good. So it turns out we found our second constant of integration. C2 is just going to be equal to T surface, the temperature at the surface, plus S T squared divided by 16K. There you go, ladies and gentlemen. We have our second constant of integration. Give yourself a pat on the back. And now the unveiling. Okay, there we go. We have the final temperature profile. Switch colors once again. RGB. Okay, we have our temperature profile. And that's what we were originally solving for, right? So just to give you guys, and this is good. This is great, because now I can find out a lot of other stuff. I want to find out the maximum temperature. I want to find the maximum temperature. That's what I'm looking for. Okay, how am I going to do that? I'm just going to take the derivative, set that equal to 0, okay? Remember calculus. And then I'm going to solve for r, the value of r that gives me the maximum temperature, and then I'm going to plug it back in T. Okay, plug it back in my temperature profile. Okay, that's it. That's going to be a little homework for you guys. The maximum temperature. Where does the maximum temperature occur? Okay, I think some of you can already solve it in your head, right? But give it a try. And the next thing, the overall rate of heat transfer. And that's just going to be the way I would do it. The way I would do it is I would evaluate dt dr. I would evaluate that at r equals d over 2. Once I've evaluated that, use Fourier's law. The flux is equal to negative conductivity times dt dr. Okay. Use the Fourier's law. You get the flux, and then Q, the rate of heat transfer. The rate of heat transfer is just going to be the area, which is going to be pi dl, the surface area, the curved surface area of our wire, times the flux. Flux is a vector quantity, and I want to emphasize that. Okay, and so yeah, there you go, ladies and gentlemen. I hope this was helpful. And just to give you guys a quick recap, what we did. Joule heating. Keep in mind that Joule heating is one of the ways in which we can have a heat generation in our system, okay, due to electrical resistance. And I just used some physics, just basic high school physics, and this is going to be my generation term. This was my heat generation term. My assumption: steady state, constant thermal conductivity, uniform heating, only heat transfer in the radial direction, okay. My heat equation in vector notation, I simplified that, but then again, vector notation for most of us is not as helpful. So we switched to the cylindrical coordinates form. Again, cylindrical coordinates because we have a cylindrical geometry. We reduced our partial differential equation to an ordinary differential equation. Integration and boundary condition gives us the temperature profile right here. So there you have it, ladies and gentlemen. I hope this was helpful. And yeah, thanks for sticking till the end. Bye-bye.